Hello everyone! This time we'll create a shader that simulates playback from a faulty videotape. Yes, it's a simulation of an outdated technology that's almost unknown today, but I still think it's an interesting effect that can find its place in many games. So let's get to it. I am well aware that this isn't particularly original effect, and you might remember that I've created something similar in this channel several times already. However, this algorithm will be at least slightly different in some ways, so we'll have more options when choosing the right shader for our game. But enough talk, let's start coding. So just like almost every time, I'll create a new scene, drop in the usual image from our game and apply a shader to it. So right-clicking the scenes folder, create a new scene, and let's call it VHS distortion. Okay, sure. And the image should be here in textures, and it's called found in JPEG. Okay, so the Sprite 2D node was automatically created, and in the inspector we'll do the usual stuff. So in the offset, let's cancel centered and transform position reset to 0, 0. And of course, scrolling down to the material section, creating a new shader material, click, and a new shader, which is type shader, mode canvas item, name VHS distortion.gd shader, and I'll put it to the shaders folder. Create and click again to open it in the shader editor. And as before, we'll start by deleting what we don't need in this tutorial, so that only the fragment function remains. Deleting vertex, deleting light, and saving. Okay, this time I decided to use only the most basic parameters to control our effect. Later, you'll see that the code contains various numerical constants that I created through experimentation and that you can replace with additional uniform parameters. However, it's not necessary, and I think they don't have a significant impact on the final effect. So, the uniform parameters. I will have only two. The first will control the speed of the effect, and the second is the intensity, like this. Okay, so uniform float speed with a hint range, and the initial speed I'll set to 2, and the range would be from 0 to, let's say, 10, and the step point 0, 1. Okay, the speed of the animation and the power of the distortion. So uniform float power with another hint range, and the initial power I set to, I think, 0.25. And this time the range goes from 0 to 1 with the step point 0, 1. As you may guess, we'll once again need some kind of a pseudo-random function to achieve a certain degree of variability in the simulated distortion and other visual defects. I'll insert a function we know well from previous tutorials, one that returns a pseudo-random value in the range from 0 to 1 based on the two-dimensional input vector. This one, #12, as surely we've seen in many previous tutorials. So this function was sufficient for simple effects such as the horizontal jitter I created here recently. This time, however, we'll need a slightly more complex and smoother function that better approximates the expected image displacement. I'll create a new function called noise12, which may resemble the algorithm known as parallel noise, but it's a simplified and more efficient approximation. So let's do it here. Float noise12, and again with the input parameter vec2, let's call it p this time, for point. And first we'll create a 2D grid of our screen, which is based on, as we know from previous tutorials, floor and fract function. So first, let's create a vector called I, which is a result of floor of B. So the integer part of both components of this vector, and now the position inside the cell, which is vec2f for fract, and it's a fract function of B. So it goes from 0 to 1 in both dimensions. Now we need random values at corners of the cell called A, B, C, and D. So this, and now in I, this is the first corner. Then for the other corners, we will just add a two-dimensional vector with these coordinates. Float B is #12 I plus vec2 of 1 and 0. This is the second corner, and now I'll copy and paste to save time for C and D. And the vector is 0, 1, and finally 1, 1, which could be shortened as 1, of course. Okay, and now we need something like a fade curve, which is similar to a smooth step function, and it would look like this. Vec2, let's call it U, it's a pretty short, is f times f times 3, that should be open bracket, 3 minus 2 times f, and yeah, that's it. Okay, and finally we need to return something, and to smooth everything out we will use the method called bilinear interpolation, which is a combination of mix functions like this. Return mix of mix a b u dot x as the weight factor, and the second parameter is mix of c d and again u dot x, and finally u dot y. Yeah, that should be it. Okay, something is not correct. Let me fix what is not right. A b u dot x c d, yeah, of course, dot, not comma. This is correct. So with the preparatory work done, we can move on to implementing the fragment function. I'll start with the usual assignment of UV coordinates and setting the time variable based on the internal time and the speed parameter. So let's get rid of this command, and vec2 UV is the internal UV, and float time would be time times speed. As we've seen, the effect is based on shifting the image horizontally, so we'll need to modify the x-coordinate of the current pixel. I'll prepare a new variable, which for now won't apply any shift, so it will be very simple. Float x is just uv.x for the time being. Then we retrieve the pixel color at the new coordinates. So vec3 color is texture on our background image, and the coordinates are vec2 x and uv dot y, and of course just RGB components because we assign that to vector3 variable, but texture returns vector4 including the alpha channel we don't need right now. And finally we'll need to assign the resulting color to the color variable, which is the output of the fragment function. So color equals vector4 for color, first three components, and 1 for the alpha channel. Okay, of course, for now we won't see any change because the x-coordinate hasn't been shifted. So let's add the first part of the effect, which is based on large waves created thanks to the fact that the noise12 function works with smooth pseudo-random values. Okay, and I'll do it right here before this. So float, let's call it slow noise, is function noise12 applied on vector 2 and time, and now UVY times 0.3. Okay, and now we need to do some other improvements. Slow noise is max of 0, so we don't get any negative values there. Slow noise minus 0.3 divided by 0.7. Okay, the overall displacement will consist of several components, so we'll create a variable for it, and for now I'll assign only the slow noise to it. So it would be float noise is just slow noise. Okay, then we can update the definition of the x variable, this one, by subtracting this noise from UVX and squaring the noise to make it stand out more, and then multiplying it by the power parameter, which controls the overall image distortion. So it would be x UVX minus power of noise to the power of 2 multiplied by the power. Okay, and I think we can already see something. Let's show the whole image. Notice how the distortion really occurs in smooth waves. There is no jittering or similar interference. We can demonstrate the difference between noise12 and hash12 if we temporarily use hash12 in the definition of slow noise. Where is it? Here. So instead of noise12, I'll rewrite it to hash. Okay, and now we can see it's definitely something like a jittering. So let's revert to our noise12. Much better. By the way, as I mentioned at the start of this video, these constants like 0.3 and 0.7 are definitely candidates to be converted to uniform parameters if necessary. But right now, let's work with them because I think that as a result of my experimentations, these values give the best result. Okay, so I think it was quite illustrative to change it to hash and then back to noise. Let's continue with the code by adding faster waves. It will look like this, and again, I'll use more constant that can be later replaced with parameters, but now it's not necessary. So after slow noise, I will add fast noise. Float fast noise is, again, our function noise12, this time applied on different parameters. So vec2 time times 10 to make it much faster, and uv.y times, I think I used 2.4, okay, and minus 0.5. All right, this is the first part, and I guess I needed to decrease the value by multiplying that by 0.15. Okay, so we defined the fast noise, and now I will add it to the slow noise plus fast noise. Okay, and wait for it. Is something happening? No, sorry, this is multiplication plus, of course. Now it's correct. We can see that combining both wave types gives us a much more realistic effect. But we are not done yet, because the real VHS noise would include not only image displacement, but also pixel breakdown and the typical horizontal stripes. So let's move on to the second half of the algorithm. I'll start with the horizontal stripes, which will render in grayscale based on the values from our hash12 function. Yes, this time it's already hash12, not noise12, because for stripes of this type, we actually need larger value fluctuations. And finally, we'll blend the grayscale tint with the original pixel color, like this. Okay, so let's find the color definition right here and let's add the stripes as I mentioned. Let's call it interference flow. Interference is hash12 applied on vec2 0 and uv y times time. Okay, so we can see that the x-coordinate of this vector is constant, 0, because we want the same value over the whole line to make the stripes. And let's mix it into the color. So color would be mix of original color. Now we need a grayscale based on this interference value. Interference. And the weight factor is our noise value. Okay, it seems the noise value is too large and the stripes are covering too much of the original image. So let's reduce it. Noise times 0.3, for instance. Okay, that's better. By the way, this constant again is a good candidate for an additional uniform parameter if we wanted to control the overall intensity of the stripes. So the stripes look good, but they would look even better if we added a repeating pattern to simulate the scanlines typical for old CRT screens. We'll do this by slightly darkening every fourth row. The step function will help with that. As we know, it returns 0 or 1 depending on whether the second parameter is smaller or larger than the first one. So I'll add it after that, and let's call it scan float. Scan is step of 0.5, and now I will write something new and then explain it. Frag chord dot y times 0.25. Okay, so you might be wondering why frag chord is used here instead of UV coordinates. Well, the reason is that frag chord works with the actual dimensions of the image, meaning that in our case it returns values from 0 to 1079 in the vertical direction along the y-axis, while UV is always normalized to the 0 to 1 range. So if we want to detect specific rows with pixel level precision, frag chord is more suitable choice. So, and we divide it by 4, like multiplying by 0.25, which gives us exactly what we want, every fourth row. All that's left is to use the obtained value to adjust the final color. And again, the constant 0.3 I will use could be easily turned into a new uniform parameter. So color is multiplied by 1 minus scan times noise times 0.3. Okay, and as the final enhancement, we'll add chromatic aberration, that is, a slight separation of the individual color channels of each pixel. This effect also results in a certain loss of color saturation, which is again typical of heavily used VHS tapes. So I'll start by defining the offset for the green and blue RGB channels using a reduced value of our noise. Let's do it here. Float shift is noise times 0.5. Next, we'll sample the green and blue components of the pixel at the shifted x coordinate. So float G for green would be texture of our texture, and vector 2 x plus shift and uv dot y and the G channel. So this is the first, and now the green part, which is very similar, B here for blue, blue, and this time we are moving it in the opposite direction. So X minus shift and UV dot Y. Okay, and then we'll blend these results with the red channel, giving the red component a higher weight in the overall mix to achieve the expected look. Color dot what? G is a mix of color R, the red component, and our G value and 0.25. So it's closer to the first value, which is red. Okay, we already see something, but that's only the green channel. Let's do the same for the blue one. Blue and the B value, sorry. Okay, and we are done. Once again, we can identify good candidates for additional uniform parameters. This reduced the value 0.05 for the offset strength and 0.25 for the color mix. Notice that if we only want distortion without displacement, we can set the power parameter to 0. So I'll open it in the shader parameter and drag to 0, and now it's only using the chromatic aberration and the stripes. But even so, I think the effect looks better when it displays all the characteristics of full image deformation. As always, thank you so much for watching and for every like or subscribe if you enjoyed the video. If we want to gain more control over the effect, we can replace the internal time variable in our game with a value sent from a script, but that belongs to the kind of improvements that anyone can try on their own. Of course, I will add this shader to the Godot shader pack as a free update for everyone who has purchased it. For now, once again, thank you for watching, have a great day, good luck with your projects, and I'll see you in the next video.